Okay, so I'll just record it as well, just for the people who can't make today. Okay, so whoops. Hey, great. So the first thing I wanted to talk about today was a technique that I mentioned in the second the second session that was rescheduled to today. So this technique is called enveloping. So I'll just show a whiteboard here. Okay, so enveloping is a technique when you're sketching graphs where you can use, let's say I have a function y, and let's say it's a function of x times maybe cosine of x or sine of x. So what this technique uses, so again, for a lot of you, if you can remember this from the last session, whoever came, what this technique uses is that we draw our function. So we draw f of x. So it might look like this. And then we draw minus f of x. So it could be that this was f of x, and this could be negative of f of x. And what we use in this property is the fact that at some points, sine of x or cosine of x are equal to 1. And at some points, they might be equal to minus 1. So one of the examples I gave is something like this. So I'll give an example of y equals 1 over x times cosine of x. So I'll just write that here. So what we'd have to draw is the 1 over x graph, which I'll draw in red. And then I'll draw the minus 1 over x graph in dotted lines in green. This is minus 1 over x. 1 over x. So essentially, can anyone tell me, when does cosine equal, like at what values does cosine equal like positive 1? Does anyone know? Yeah. So let me just check. So yeah, so you got 0. So yeah, you got x equals 0, any other value. So x equals 0. Yeah, 2 pi. Good. So x is 0, 2 pi, 4 pi, and just carries on. So I know when I put x equals 0 or 2 pi or 4 pi here, the cosine value will just be positive 1. And then because that's just 1, it will just be a 1 over, let's say 2 pi or 1 over 4 pi. So that means that I know this function will be on the 1 over x graph at each 2 pi. So let's say it's at 2 pi, it's here. And then at 4 pi, it will be on here. Then at 6 pi, it will be on here. And then same for when I go for, let's say, the minus 2 pi, minus 4 pi, minus 6 pi. They're multiplying by 1. So they're just going to be, again, on the 1 over x graph, like here. So minus 2 pi, minus 4 pi, minus 6 pi. And then when is cosine equal to negative 1? Can anyone tell me when is cosine equal to negative 1? So pi, 3 pi. Good. So what multiples of pi do you get? Do you get negative 1? What types of multiples? Yeah, odd. Yeah, good. So you got odd ones. So I know if I'll draw these in a different color. So I'll go pink. So if I go for 3 pi and 5 pi, let's say 7 pi, these are all going to lie on the negative 1 over x graph, because they're going to be when cosine is equal to negative, and then negative 1, sorry. So minus 1 times 1 over x, we get minus 1 over x. So I know these ones are going to lie on here, and here, and here. And then when I go for minus 3 pi, it will be on the minus 1 over x graph in green, minus 1 over x, and then minus 1 over x in here. So what we can do now that we've got these, at least, is we know this function will just will oscillate kind of like cosine, but it's been enveloped by this 1 over x graph. If we put this in, so if we put in our final value, we know that at let's say, oh sorry, I think I missed at pi as well. So I missed pi. And then minus pi. So that will be here, and then that will be like somewhere around here, let's say. Okay, so what the graph will look like is like this. So it'll start coming in from, let's say, it'll start coming in from infinity on here. Then it'll cross down at like pi over 2. Then it'll touch this point, and then go like here. Whoops. Then go like that. Oh, that's really bad. But basically, it should cross at like the pi over 2, and then go through 3 pi over 2 back up to here, and 5 pi over 2 back up to here, 7 pi over 2 back up to here, and then there. And then kind of go like that. And then same for this one. So on the other one, when you got the negative x values, then it would just start following a similar pattern. Like that. Oops. So, like you can see here, this is what it looks like. So it looks like cosine, well, kind of like cosine, but it's been enveloped by this function 1 over x. So I've drawn 1 over x and minus 1 over x because I know at certain points it's going to be on those functions. It's going to be on those envelopes. Now, before we move on, does anyone have any questions that they wanted to raise or anything they don't quite agree with? So is there anyone who's got kind of any confusion on this technique? No. So no questions so far. Okay. Okay, actually, okay. So I think there are some questions. Yeah, so you only use this for multiplying. Yeah, so you only use this for multiplying a function with a trig function. Yeah. And what is it used for? So yeah, this is mainly used, this is an interview style question. So when they give you, for interviews for practically all of your subjects, they will give you graph sketching questions. I know Elisha's asked about what it's used for. It's actually a really pointless technique. They mainly use graph sketching questions just to see how you think about functions and how you can, like draw them. So really unfamiliar stuff. So this is one of the examples that they could give you. Sometimes it might not be like, function times a trig function. They might give you, let's say it could be an exponential, then divided by x, and then times something else. And then you couldn't use this technique. But it's mainly to get used to the fact that they give you unfamiliar functions, which are made up of familiar functions, and how you can try and combine them to make one whole function. So yeah, it's a very specific technique when you've got a function times a trig function. So it could be like sine or cosine. Obviously, it'd be something different if you use tan of x, because that doesn't have kind of the same properties. And I believe, yeah, graph sketching questions come up in almost all STEM subjects. If you do maths, computer science, engineering. I think chemistry a bit less so, but they can ask it because it can come under the kind of physical chemistry side. And yeah, physics and engineering will use it quite a lot. it's kind of, it is, again, I'll just reiterate, it is a very pointless technique, as in, because when you get to university or anything like research, if you want to draw a complicated graph, you just put it into a computer and then it will plot it out for you. But this is just to get you to know, like, oh, if you're what you should be expecting if you drew something like this. So there's no actual like real world use. It's more so just so they can see how you think when constructing a graph. Okay, so I think one of the ones I wanted to mention, so see if anyone could work this out. So if I gave you something like a sine of, let's say sine of 20x, and sine of x, which one could we draw as the envelope? And then which one could we say is kind of inside? So does anyone have an idea? So anyone who didn't attend the other one where we kind of covered this, anyone have an idea which one would be the envelope? Oops. Okay, so Abir, you say it's sine of 20x. So I think two of you are saying sine of 20x. So does everyone else agree? So you do sine of 20x. Sine 20x. Okay, so everyone's going for sine 20x. So actually, you wouldn't use that one as the envelope. The one you'd use is sine of x because it varies less. So normally what you'd want to use is the one that varies over a larger kind of range. So sine of x would be like more slowly varying. And then sine 20x would be like, you know, so you'd essentially want to use the sine of x, say like that. Just wrong cosine. So you'd want to use something like sine of x, like this, and then you would also draw minus sine of x, like we said before. So you draw minus sine of x. And then what you'd use is when does like sine, and then you'd have to use specific values. So when sine of 20x equals like positive and negative like 1. So it could be, so yeah, so I could say, when does sine of 20x equal positive 1? Can anyone think of the first value when it equals? So when would sine of 20x equal positive 1? So what would 20x have to equal inside? Yeah, half pi. Yeah, so it would come up at half pi. So 20x would equal half pi. So then this would be pi over 4. Yeah, 1 over 40 pi, as people are mentioning. So it'd come up at 1 over 40 pi. And then the next one would be 3 pi over 40. That would be when it's negative 1. And then you go 5 pi over 40. That one when it's positive 1 again. So what you could see here is it should look like this. Then like that. So you get this kind of beat pattern, essentially. So in this case, it was easier to use sine of x as the envelope because it varies like less, whereas the other one kind of oscillates very rapidly. It'd be harder. So if you use sine of 20x as the envelope, so you could try that, but you'd find that it's kind of really hard to draw sine of x inside that. So it's usually easier to draw the function that's more slowly varying, essentially. Okay, are there any other questions on this technique? So it is a really specific technique, and they won't always ask these kind of questions, but they will generally ask general graph sketching questions. So yeah, I think Jack, you asked about what about tan functions. So tan functions involve using, you know, things like let's say you know they've got asymptotes, so you could draw the fact that at pi over 2, at pi over 2, then 3 pi over 2, those kind of values, you should get like infinite values. And then there's not really a technique for the tan functions, but you just have to use properties of it. So you'd have to say, okay, we know it repeats every pi. We know that it's got asymptotes at certain points. We know that, oh, you could also say, you know, that it's equal to 1 and -1 at certain points as well. But it's a lot more, yeah, but it's a lot weirder, I'd say. So you could try and plot it out. So you could try and use a function and then use like tan x times that function and then try and see, are there any points that you know for sure? But yeah, graph sketching as a technique is very useful for them to assess how well you understand the functions. So one thing I recommend when you're doing graphs, so not just these cases, but any types, and they ask you to draw them, you basically want to think of the functions that you know. You want to mention, are there any certain properties? So you want to really state the obvious in your head so you know these inside out. So sine of x, I could say sine of x is anti-symmetric. So it looks different on one side than the other, like the opposite. So like when x is positive, let's say x is pi over 2, sine of x is 1. So I know when sine of minus pi over 2 is like -1. So I know it's anti-symmetric. It looks completely opposite on the other side of the y-axis. I also know that sine is bounded by 1 and -1. So I know that feature. I know sine is it repeats every 2 pi. And yeah, things like that. So you kind of want to make it as granular as possible. You want to say for certain functions, okay, I know all these properties. I could say if I wanted to draw a logarithmic graph, then I could say, okay, I know a logarithmic graph equals 0 when you put x as 1 in there, because like log of 1 for any base would equal 0. I could say a logarithmic graph also has a decreasing slope. So the slope should get flatter and flatter as you go, because as you increase x, then the increase in the log function won't be as drastic. And yeah, and then so you just essentially want to mention special features and things that you notice of functions. They don't have to be kind of they don't have to be very like special parts, but just things that you know are quite unique to that function and things that are important. Hey, so yeah, the graph sketching, like we'll be doing plenty of graph sketching over the coming months, so it's good to keep practicing the technique. So this is just one technique called enveloping, which can be used. But normally you want to look out for things like symmetry, asymptotes, like y-intercept and x-intercepts or roots. And you may also want to look for like gradients. So normally I use gradients as a last resort. Like if you differentiate and then you see how the gradient changes, you can have an idea of like how the graph varies, essentially. But yeah, we'll be practicing these a lot over the coming months, so I wouldn't worry too much about it yet. And any questions before I move on to just the next part of the topic? Does anyone have any other questions? Nope. So no questions. Okay. Okay, so I think someone does. So, Chakshu, what's your question? So do you think? Oh, sorry. So I was just going to say, yeah, so this technique I would recommend for all of you because it will be important for interview practice. So it's not so relevant to, your admissions tests, but it will be relevant for interviews because they almost always, if any of you, when you get to the time you watch mock interviews for Oxbridge, you'll notice in almost all the mock interviews they mention graph sketching questions. It's just such a common type of question that comes up. Okay, and okay. The next part I wanted to mention was this thing called the Taylor series. So I mentioned this in one of the kind of homeworks of the very first session in case anyone wanted to read up. And the Taylor series, I don't know how much anyone knows about them in here, but they're very useful for approximating or writing different functions in terms of just, powers of x or polynomials. So you could have a really complicated function. It could be like sine of x or cosine of x. It could be like an exponential function, like 2 to the power of x. And you want to find out how you could write it maybe as a sum of different powers of x. So one of the examples I'll give here. So this is what we posit. So let's say I have a function of f. Its Taylor series would be f of a point A plus the first derivative times x minus a plus the second derivative at a point A, and then x minus a squared. So I should write that plus 1 over 3 factorial, the third derivative at a, x minus a cubed plus dot dot dot. So this carries on kind of like infinitely. So if your function can differentiate, like so on and so on, you can do this. So I was just going to say this technique is used especially in so I think as I mentioned to Serki like in one of the first sessions, the technique and this thing seems kind of pointless, like why would you want to do this? But this is actually how calculators work out your certain like functions. So there's no kind of special function like sine and cosine that you can put in and a calculator knows exactly what it is. Like what it has to do is it approximates it using a Taylor series, and then you work out and then you can work out the values of like sine of x at a certain point. The way to understand this intuitively is like if you ignore all the faff on the right hand side. So I'm going to kind of say ignore this side on the right. So just focus on this. What kind of approximation is that? So you've got f of a, which is just a number, and then you've got f dash a, which is again some other number like f prime a. You got x minus a. Does anyone know what this is kind of? How is this approximating something? Like what kind of approximation is this? Just this first part. Can anyone guess? Anyone have a clue? It is because it is quite like it's very abstract the way it looks right now. But this essentially is saying, imagine you had a function. Imagine you had a function, and it might look like this. So I start at a point A. I could start at a point A, like let's say x equals a here. And if you wanted to find out maybe what is this point, like over here, like your first port of call is maybe to approximate it as a straight line. So you'd start with f of a. So you'd start with f of a, and then you'd put plus f prime a, which would be the gradient, then times x minus a. So it's basically you're starting at this point f of a, and you're adding however much you should be going to there. So this first part is saying, okay, I want to approximate my function, like just maybe in this area, I just want to approximate it as a straight line. And then maybe if you want to be a bit more accurate, you add the next part, which is, okay, I want to approximate it maybe as a quadratic. And the next part is I want to approximate it maybe with a cubic. And then you keep adding like, higher and higher powers. And then you're like, okay, once I've added enough of these, I've got a really good approximation for my function. So the first part, if you just look at f of a, that's just if you just said, okay, if you're really lazy approximating it, you just wanted to say, okay, all of these values are f of a. But then your next part is, okay, if I want to be slightly more accurate, I could approximate with some straight line with this gradient and then work out the next point. So the Taylor series is essentially able to work out. So using just the derivatives or like differentiating at one point, you can actually work out what the value of the function is at different points of x. And they might not even be very close. They might be like really far away. Okay. Yeah, so do we just choose a random value for a? Yeah, so it's completely arbitrary, but it depends on the application you're using. So if you're like, it depends on what you're doing, but it could be like, okay, I could say a is like 100. Let's say you're trying to model a hill. Let's say someone says, okay, I want you to make this model of a hill on a computer. And you could try and approximate the function. So you could say, okay, I'm going to pick some point to start from, and then I'm going to draw the hill around this point and what it looks like and how it curves, essentially. So yeah, this is called the Taylor series, and I really recommend you read up on it because it has numerous applications in the sciences, and mathematicians use it especially for functions when you want to find out like behavior at certain points, essentially. So will this be useful for interviews? Yeah, so the Taylor series itself, it's useful normally in interviews. It's useful for finding things such as limits. So it's useful for finding things such as limits. So it could be, so I'll just mention, let's say sine of x. Let's say our function is sine of x. Then I don't know how far anyone's read ahead, but I don't know how far anyone's read ahead. Does anyone know what the sine of x differentiates to? I don't know if anyone, depending on how your school does your A levels, does anyone know what sine of x differentiates to? Anyone? Yeah, I guess not. But basically, sine of x actually differentiates to cosine of x. Wait, yeah. Oh no, for, I think if that's Jaden, cosine differentiates to minus sine. Sine of x differentiates to just normal cosine. Cosine of x. And then, yeah, and then this differentiates to negative sine of x. And then this differentiates to negative cosine of x. And then this goes back, and this kind of goes back in circles. This goes back to sine of x at the fourth derivative. 1, 2, let me put IV. Yeah. So sine of x differentiates to these. If you check my OneNote, so the OneNote link I sent, I actually show how you can differentiate sine. So things that you need to know are like geometry, some geometry, and like you need to learn. There's a part I wrote about double angle formulas. So there's a section on double angle formulas which you need to read beforehand, and how you can get them. They just use GCSE maths. A lot, and like all these derivatives you can actually get from just GCSE maths and GCSE level knowledge, but just using a kind of like very creative way. So yeah, the sine of x differentiates to cosine of x. So would anyone like to pick? So you could pick any value. Pick like a kind of reasonable value. Would anyone like a pick an x or an a that you'd like to expand about? Yes, 0 or pi. So what would people prefer, 0 or pi? Like which one? Okay, we could go for 0. Like 0 is a common one. So 0 is a common one. So I want you to work out. So we picked, yeah, 0. So let's say a equals 0. So could anyone tell me what f of 0 is? So we're going to do f of a. What sine of 0? Sine of 0 is 1. No, sine of 0 is 0. Cosine of 0 is 1. Yeah. So yeah, f of 0. What about this one? So f dash of 0. So what is cosine of 0? If we put it here. Yeah, 1. Okay, what about for this one? What's minus sine of 0? So if we put 0 into the second derivative, what's 0? Yeah, 0. And then what about this one for the third derivative? Sorry, this does get like really tedious. But yeah, negative 1 here. So what you can do is if you put this back into the function, like here, if we put this back here, we would get f of x equals f of 0 plus f dash of 0 times x minus 0, so it's just x, plus 1 over 2 factorial f double dash of 0 x squared. So I'll go 1 over 3 factorial f double triple dash of 0 and then x cubed. And then I can't be bothered to like carry on any further, so like this will be good enough. Yeah, so thanks everyone for putting it in the chat, like these values. So does everyone, so hopefully everyone remembers, but I'll just refresh going on to the other page. So we went 0 and then 1 and then 0 and minus 1. So 0, 1, 0, minus 1. So this is equal to 0 plus 1x, so x, plus 0, and then plus minus 1, so minus 1 over, anyone know what 3 factorial is equal to? Yep, 6. So -1/6 x cubed. So we're going to use this to approximate sine. We're going to use this to approximate sine. So we're saying sine of x is roughly, like near x is equal to 0. We're saying sine of x looks like this, like x -1/6 x cubed. So I'd like if any of you have a calculator near you, I don't really have one because I never really use one anymore. But if you put in x so we're saying we're approximating kind of close to 0. So you could pick x equals maybe 0.1. I could pick just x 0.1 as a rough value. So I'd like you to say what is sine of 0.1 equal to, and then I'd like you to say what is 0.1 minus a sixth of 0.1 cubed is equal to. So I'd want to compare like the values of each. So can anyone tell me what sine of 0.1 is? In radians, by the way. This is all in radians. So this is, 0.0998. 0998. And then what about if you put it into the other one, into the other function? So 0.1 minus a sixth of 0.1 cubed. Yeah. So you also get about 0.0998. Okay, so yeah, thanks for that. So you can see they they approximate it pretty well. How this was gotten? So it was a guy, a person called Brooke Taylor back in the day, like approximated these. There's 2 ways to kind of think about it. So like just to make sure I'm not, just lying to you or pulling stuff out like thin air. Like one way you can think about it is if you were gonna if you wanted to find a function, you wanted to write its polynomials, then you could say, okay, when I put in x is equal to a here, everything else goes away. When I put in x equals a, like everything else goes away and you just get f of a here. So you get f of a is equal to f of a because all these go. And then when you differentiate it, the constant part goes, like f of a goes. And then you get f dash of a on its own, plus a bunch of other things carrying on. And then you could put x is equal to a here. And then you end up getting like f prime of a equals f prime of a, and then you could carry on. There's another way to show this Taylor series as well, but it uses kind of an A2 technique, which is known as like chain rule and integration by substitution. So these will use kind of A2 techniques to show it. But if you want to read on, like you could say, okay, how is the Taylor series derived? Like you could check. So just to make sure I'm not lying to you, because you can't trust everything I say as much as you might want to. But yeah, this is a legit technique for approximating these functions, and it's really cool how it's used. So if you plan on going, even if you're a mathematician planning on going maybe into theoretical physics or maybe even theoretical chemistry and like chemistry side of things, sometimes you can approximate like potential energy using some Taylor series. So like just to give a practical example, it might be that you have maybe like hydrogen and chlorine like in a bond, and then you might find out let's say you might find out, okay, actually I won't give that, I'll give like oxygen and hydrogen in a bond. And then you might try and find out, okay, when they're at different distances, what's their potential energy? Like, what's their potential energy? So when they're at different distances, their potential energy might look something like this. So potential energy looks something like this. And then this is against x. So this is where x is the distance. So why is this useful? Well, the Taylor series says that your equilibrium, so where they're at equilibrium, will be where the potential energy is lowest. So like at the minimum. So if you got the potential energy, how would you find out where the minimum is? Like, can anyone tell me? How would you find out where the minimum is? So if I gave you potential, yeah, I think someone's written. So, oh no, that's not a root. So it's a root of what though? So how would you find out where the minimum is? Anyone know from their AS classes? How would you find out where the minimum is? Yeah, the root of the derivative. Yeah. So if you got the function, you could differentiate and then set that equal to 0, and then you can find out where the turning point is. Yeah, yeah, good. So you've all got that. And then what you could basically do is find out, okay, now we've got this function, but we only care about what it looks like around this area. So we only care about what it looks like around this area. So you might zoom in on here. So if you zoom on here, you could say, oh, this kind of looks like some kind of x squared, like some kind of x squared graph. So you could approximate as a parabola. So you could approximate this as a like parabola, like around there. So can everyone see that? Like, does that seem believable that you could approximate kind of like a x squared graph just near here, just near that region? I don't know, does anyone like disagree that it doesn't look anything like an x squared graph around there? Yeah. Okay. So I'll take the silence as everyone kind of agrees it looks almost like an x squared graph there. But basically, what you find out is when you approximate as a parabola for the potential energy, so it's something like something x squared and whatnot, then you could work out essentially that this bond, this oxygen and hydrogen, they might oscillate around here, like around where they're at equilibrium, they might oscillate. And then this is why you get rise to, I don't know if anyone does chemistry here, that's how you get things such as infrared spectroscopy. So approximating it using a Taylor series, like you can find out like how the bond oscillates, like what frequency it oscillates at. And then that will tell you what infrared radiation it might absorb. So that's useful in things such as like global warming, like why does carbon dioxide absorb certain types of radiation or like infrared. So that's a practical example, a practical use of the Taylor series for this. But yeah, if for a mathematician, it's mainly for finding limits and things like that. So okay, so does anyone have any questions on that at all? Anyone have any questions on like the Taylor series in general? No. Okay. So yeah, but yeah, if you're still confused, like please do feel free to ask me like either privately or like on the chat if there's anything you want to like clear up. But yeah, it's a really useful technique. And so yeah, for like interviews, it'd mainly be useful for limits and also like approximating functions. So it's really really useful in that way. Okay. Oh, okay. So can you show an example of finding a limit with it? Yeah. So I just wanted to give one, for example. So we are going to breakout room soon, by the way. So it's not just going to be like me out of board for the whole session. So like sine of x. So sine of x, we approximated it as like x minus a sixth x cubed. And it's going to have a bunch of other things. So yeah, sine of x is equal to like x minus a sixth x cubed. So if you wanted to find out the limit of sine of x over x as x goes to 0, you could say this would be equal to x minus a sixth x cubed with some other terms which are going to have like higher powers of x divided by x. And then this is equal to 1 minus a sixth x squared. So as x goes to 0, limit equals like 1. Or this term tends to tends towards 1. So this is useful. So this can be useful in finding limits of things, because depending on different things, like you might be doing things in calculus such as differentiating and other things where you're sending something towards 0. So it can be useful for finding those. Okay. Yeah. So yeah, thanks. So so yeah, it can be useful for that. Again, finding limits, only mathematicians will really care about it. But yeah, for like other people, like they won't. So Taylor series have their other uses in like kind of the sciences that other people would find useful for them. So I think without further ado, I will set you all into breakout rooms, and I'll give you the questions that I wanted you all to try and answer in there. Okay, so I'm just trying to remember. Oh, actually, so I think I was trying to find the sheet, and I don't know. It's Sahi, do you remember? From anyone who was in the last session, does anyone remember the task that I gave as a, I think as a homework? I'm just trying to see if I wrote it anywhere here. 2014 GHI. Yeah. Okay. So good. Yeah. 2014 GHJ for them. Okay. So yeah, for mathematics and Komsky. Computer science. Then your task is to do. So yeah, I'll clarify it a bit. It was 2014, and the MAT 2014 from Oxford, like G, H, and J. Yeah, and then question 3, and then question 3 as well. So question 1, G, H, and J, and then question 3. So if you could try those questions, I think they're really good. And then for people doing physics and engineering, one question I want you to try is a rocket. So a rocket, like you can either model it launching horizontally, a rocket of mass m in total. It's made up of fuel and like metal parts. So it showed it. Yeah, so doing those now, so I'll just send you into breakout rooms soon. So a rocket of mass m, like yeah, it's trying to launch itself. So what it does is it ejects fuel at a constant rate. So it ejects fuel at a constant rate, and fuel has relative speed of like minus u. So it has a relative speed. So compared to the rocket, when it's released, when the fuel is released, it has relative speed minus u when it's released. So I'd like you to find the speed of the rocket at any time t. So I'd like you to use like any knowledge that you think might be relevant in this case. The speed of the rocket any time t. I'd like you to find out the speed at any time t, and like use any principles that you know or think might be useful in this case. But yeah, and also use any kind of approximations if you want. So if you think, okay, how could I approximate this, or what could I do? Think how to tackle it. So these are going to be hard questions, but I'll send you all into breakout rooms now. So I'm going to create 2 breakout rooms. So first breakout room is maths/Komsky. And the second one is Viz/Eng. Okay, so I've just opened a room, so please do go into them. And if you can, take a picture of the questions. Hi, Elisha. I don't know if you dropped out. Assign you there. So, Sir, are you there? I'll just assign you to Maths and Comp Speed. Okay. Breakout rooms.
You're muted, by the way.
Sorry. Yeah, so unfortunately the breakout rooms have timed out, so it's the official end of the lesson. But if anyone would like to stay on, I'm going to be here for about 15 more minutes if anyone still like would like to try and work out the questions and like ask for any help. But apart from that, there's like no obligation, you know, to stay if you need to go, or kind of can't be bothered either. That's a good excuse as well. But yeah, like feel free to stay on for like 15 more if you'd like to, but if you like rather just rest, then yeah, have a good rest of your Sunday evening. But yeah, I'll just reopen the breakout rooms for a bit more. But if anyone needs to leave, then thanks for joining, and I'll see you next time.
What is the answer to H?
H.
Yeah.
Which is it? Who's asking that? Sorry, Zisha.
Jaden.
Oh, is it Jaden?
Yeah.
11,000. Yeah, it should be 11,000.
Yeah, okay, cool. Yeah. It is. Okay,
11,000. Cool.
I got that, so that's nice.
Okay, that's good. Yeah, it's good. So if you notice a pattern, you should be pretty confident. Yeah. But cool. Yeah, I think if anyone. I don't know.
When's is it? Actually, no. Our next session will be on the schedule. Anyway, see you. I'm all done then. Cool.
Okay. See you.
See you next time.
I don't mind talking about that rocket question.
Yeah. Yeah, I think there's about 4 left. Yeah, so it's only so all the maths people left. But I think they neither can work it out. So yeah, the main thing with the rocket one, I can actually do it in the main room here, is what you have here is, let's say the mass at a certain time, and it's traveling at speed v. And then for this one, you said the mass was like m minus I delta t, right?
Yeah.
And then here, so this was traveling at speed v, and then this was I delta t. So if it's launched at relative speed, like negative u, so you know, like if the relative speed is like minus u.
Yeah.
What's its actual speed in R frame? So if you were like, if I was traveling at some speed, let's say compared to you, I was traveling at like -5. How would I get back to the frame in like someone else's reference? Like, so minus u. So no, like u is still the relative speed. So what would you need to know in order to find out like my speed? So okay, you've got 2 runners. Let's say you've got 2 runners. One is running at speed 5. One is running at speed 2. What's their relative speed? Like one's running at speed 5 meters per second. One's running at speed 2 meters per second. What's their relative speed?
3 meters per second.
Yeah. So for the person running at 5, the other person's running at like -3, right? And then for the person running at 2, the person running at 5 is running at +3 to them. So for this one, can you see you just have to add on the speed back on? So if you wanted to get so if
V take u.
V take u, exactly. So it'd just be V take u would be the actual speed. So if you were like, if one's traveling at speed, let's say v before, and then the other one's traveling at v minus u, then it will be minus u compared to them. Does that make sense to everyone?
Sort of.
Yeah. If you want to do it, like normally it's easier to do it with the numbers first, and then you could see if you could put it into algebra. But the thing is, this wouldn't just be traveling at speed v. This one wouldn't. It would have increased its speed by a bit. Like it would have, changed like by a slight bit, like to delta v. So yeah, so this is launched at u kind of relative to the like old original speed, like a bit before, something like that. So what principle did you say, like what's conserved? Did anyone like remember? What did we say was conserved?
Momentum.
Momentum. So yeah, so the momentum before was mv, and what's the momentum afterwards? So could anyone, what's the momentum afterwards? What's the total momentum if you get all these momenta?
Oh, 0.
Oh, sorry, the change. So the change of momentum is 0. But if we were working out like momentum before and momentum after, Actually, it depends on whichever way you want to do it. So, like, do any of you do it like as in change of momentum, or do any of you do it like momentum before is momentum after? Like, whichever way the people prefer.
I don't have a clue what you mean for me.
Oh, is it like sometimes people say, okay, the change of momentum 0, but then some people just be like equal the first momentum to the second momentum. They might
just
do it.
zero. Just 0.
Oh, so you're saying the change of momentum is 0?
Yeah.
Change of momentum is 0. So what the final momentum is m minus I delta t times v plus delta v. And then plus, is it I delta t times v minus v? That'd be the final momentum. So yeah, I've done the mass of the rocket, the mass of what's left times its speed, plus the mass of the fuel times that speed. Then take away mv, right? The initial momentum. Initial. And then you're saying that's equal to 0.
Yeah.
Yeah. So could you, yeah, what happens when you expand out? So what do you get?
Should end up with mv plus delta mv or m delta v.
M delta v.
Take I v delta t.
I v delta t.
Take I delta v delta t.
Yeah.
Oh, and then you expand on the side, which is I v delta t.
Yeah, I v.
Take I u delta t.
Delta t. That's yeah, I v delta t. And then take away the mv.
Yeah.
0. Yeah. So then what cancels out?
mv.
mv. Cancel out mv here. Anything else cancel out?
IV delta t.
IV delta t. So IV delta t. So you should get left with m delta v minus I delta v delta t. Then is it minus IU delta t? Equal to 0 that everyone got.
Yeah. Should be that.
Yeah. So normally what people do, but like I'll just mention, normally you'll ignore anything that's second order like that. So we call that second order when you've got like 2 deltas, like deltas times a delta something, because then we say, okay, that's really negligible, but really small compared. But if you don't want to ignore it, what you could do, okay, is we want to find out, we could say, you could rearrange this to get m delta v equals like I delta v delta t plus I u delta t. And then if you could divide both sides by delta t, right? So you could get like this, like m v delta t. What do you get on the right hand side?
I delta v plus IU.
IU. Yep. And then normally, like, what would we do? What would we do to like the time interval? Does anyone know? Anyone guess from their A-level classes? What would happen to the time interval? So like what would we
For 0.
Yeah, goes towards 0. So if the time interval goes towards 0, what happens to the the change in velocity? So if the change in time goes to 0, what happens to the change in velocity?
Is it also approach 0?
Also approaches 0, yeah. So also approaches 0. So as you change as the time interval goes to 0, so is the change in velocity. And then you get m. Does anyone know what the delta v over delta t becomes? This is normally where people trip up. Or like,
It's not 0, but it's absolutely nothing. It's such a small number, it doesn't matter.
Are you sure? Like, what about if v was like 2x and t was x? What would that approach? What would that equal?
2.
2. So you can't say for sure. It depends on how quickly one or the other like goes towards 0.
Yeah.
So what you get and the definition of this, the definition is this is what you then get as the derivative, like dv by dt. So that is what's called the derivative. Delta v goes to 0 and delta t goes to 0, you get dv by dt.
Mm.
And then what you get here on the right hand side is, can you see here the delta v part goes to 0? So this goes to like 0.
Yeah.
Plus IU essentially. So like the delta v on its own would go to 0, and the delta t on its own goes to 0. But like when you take the ratio of them, you get the derivative. That's what the definition is essentially. So yeah, so basically what you get here is ma, mass times acceleration, equals I times u, like ma. So this is just saying. So you're basically just saying the force on the rocket is equal to the force like of expulsion. So then would anyone know like how then we'd get how would you then work out velocity? So actually, if we kept it like this, like imagine we forget all this calculus rubbish. If we forget all this calculus rubbish, just keep it like this. Just pretend like, okay, we don't really know anything about calculus or differentiation and whatnot. Then like you'd still like, let's say you'd ignore this part like here. Let's say you'd ignore this part because it's so small. Then you'd say m delta v equals actually, so what we should have done here is if we wanted to work out our change in velocity, we could have divided both sides by m. So I'll ignore this term, so I'll ignore that part, and then I could just say this is I u delta t over m. So that's all I've done. So basically I've ignored this because any second order stuff always goes towards 0, like because it's so small, it normally gets negligible, and then we can ignore it. And then yeah, what you would do is a lot of computers, they can't integrate or do like basic like integration or calculus. So what you would do, and it really helps you to think as a physicist or engineer, is that you could say, okay, I'm going to just take some time intervals. Could anyone say what time interval that you pick, like a small one?
2.
2. That's not very small, is it, as a number? 2 seconds.
0.1.
0.1, yeah. So like 0.1 seconds, you could say 0.1 second. So then you could say like the change in velocity would be like I times u, depending on the rate, times 0.1 over the mass. The mass would be like, if you wanted to write an expression, it would be m minus I t, essentially. So it's like the initial mass take away whatever mass has been burned, like I times t in total, like until that point. So that would be what our mass would be there. But yeah, so essentially like the expression for the mass would be m minus it. Like you might want to check that for yourself, because again, you might not disagree with me or think, where have I pulled that out from? But essentially like, yeah, all this is like capital M is just a total mass to begin with, and then take away it would be like how much fuel has been burned, like I times t, the rate at which it's burnt times the time it's taken. M minus it would give you the mass that's left at some time. And then what you could do is you could try and draw a graph. You could try and draw a graph, and you should get something like this. It should start at 0, and then it starts increasing. Oh, actually, sorry, it's the other way. So it starts increasing like that. So you could actually check it. So if any of you are like into computing or anything, you could try and draw, like check what it looks like if you keep doing that. But yeah, that was just an introduction to it. It's if you want to read more on it, it's called the rocket equation. If anyone wants to like read more, or is like even more confused by the end of this, it's called the rocket equation, and it comes from like conservation of momentum. But yeah, any questions before finish up?
No, all right, no. Thank you.
Yeah, no problem.
Next week, if it's next week or week after, I don't know, but yeah.
It's what?
I don't know if it's next week, next one, or
for like our session. Yeah, I think it should be in 2 weeks for that one.
Oh, right, okay.
Yeah, but yeah, no. See you all. Hopefully see you all soon. Yeah, have a good rest of your Sunday. And yeah, feel free as always to keep asking any questions on WhatsApp if you need.
Thank you.
Thanks everyone. Bye.